it's
Is it refillable?
refillable.
Oh, that's cool.
Yeah, water hold division down.
Can I have some?
You can buy them with money from stores.
Yeah, you can buy them. Look, it says property of Lapuz.
Oh, that's so
Cute.
I get it. Think of how many injuries you might prevent in the STEM center for me, like, this is a useless pen.
Or you could just not throw them.
Exactly.
All right,
Being realistic.
chapter 3 is about determinants. Determinant gives a scalar value to a matrix. You have a matrix, and then you kind of it's like saying if you have a vector, the length of a vector gives you a scalar value. It's not necessarily the best type of measurement, but it tells you something about the particular determinant. Yeah. So remember the big long thing with the inverse matrix theorem or something like that. So it has something to do with determinants not being equal to 0. And if determinant's not equal to 0, then there's a lot of things that follow. Yeah.
So it's you can do linear independence and dependence with determinants. Can you?
Yeah, you can. Actually, you can look online.
Before you do
What?
before you do any like
Determinant is a value that can be computed from the elements of the square matrix. That's really all they say, right?
very informative.
So let's see. So the determinant of a 2 by 2 matrix is something that we've seen before, right? So the notation, sometimes they use DET in front, or they just use a vertical line, and that vertical line allows you to, or kind of shortens the notation. Instead of having to write DET in front, you can just say that. And the DET, the determinant of this is going to be AD minus BC. So that's old news. But now we're talking about trying to extend this. And one way to extend this is to, well, next to a 2 by 2 matrix, we can look at a 3 by 3 matrix and see how to take the determinant of that. So I don't know if this is called a definition. Doesn't say definition, so let's just say the determinant. And for this, I'll get a little messier with the notation. I'll use subscript instead of A, B, C, D, E, F, G, whatever comes after that. So I'll use the subscript notation, and wherever you are, there'll be 2 subscripts. So A11, A12, A13, A21, A22, A23, A31, A32, A33. And the way we're going to do this is we're going to, what they call is expanding by one of the rows or columns. So, and expand. Expand by the first row. And that means we're going to run along the rows here. And from there, we're going to create submatrices. We're going to create submatrices that we're going to multiply this by. So I'll start off with like the notation here. This is going to be A11 times, and then we're going to call this A11 with a capital A, where A11, the smaller a, is a matrix obtained by crossing out the first row and first column of the original matrix. So this is the first row and the first column, and if we cross those out, what we have left is a submatrix that we're going to use for this. So I'm going to leave a little bit of space here. And say that what this is going to be A22, A23, A32, A33. And you may have seen something like this if you've taken Calc 3 already, when you guys are introduced to the cross product or something. You may have seen something similar to this. The other important thing is that as we're running along here, there's a sign change, and I think we've talked about that. Each element here is assigned a sign. It's a positive sign or a negative sign that kind of alternates throughout the whole matrix. And if you want to think about it as some sort of a pattern, kind of would look like a checkered pattern. If you color one of the plus signs one color, if you color the minus signs another color, then each of these things will have a checkered pattern. Basically, you'll be switching, and the only thing to remember is that very first one, the upper left-hand corner, is a plus. And then as you move along horizontally or vertically, you switch signs. So they have a sign assigned to each of these elements as you're expanding it. Yeah?
Okay, so is that to say that if you were to expand along that row, and that matrix, that inner matrix that you've defined in the red, that those values A22 and A23, for example, will have a positive and negative value at those places?
No, we're only going to consider the what we're expanding on, the numbers that we're expanding on. So after we've expanded, then we don't put signs on this anymore.
Okay, so then it would just be the values within
The
that
values
space.
of the, yeah.
Okay.
Yeah.
Oh, wait, is it that single entry times the matrix or times the determinant of the matrix?
Times the determinant of the matrix. Wait, let me see. Yep, determinant. Thank you. So determinant A11, so I take away the DET and put vertical lines here instead of the brackets. And let's keep the arrow coming from here. All right, so keeping the pluses and minuses in mind, you can put a plus on the first one, although generally you don't add that on, but for sure the second one is going to be a negative sign because we're expanding through that row, and that's a negative. here we have A12 times the determinant of the A12 matrix. So what is that? Again, you cross out your row and the column that you're in. And so here we have these 4 elements left. And those are the 4 elements that will go into this determinant that we're going to be looking for. So this is A21, A23, A31, A33. Determinant. Okay? And then the plus for this last one. And here we have our A13 times determinant of the A13 matrix, which is the matrix that we get if we cross out the first row and the third column. So crossing out the first row and the third column, we have this matrix left. A21, A22, A31, A32. Okay? So the idea is that by the time we get to this, we know what the determinant of the 2 by 2 matrix is, so we can just figure that out. So this is a formula that you probably don't want to memorize, but if you're good at memorizing formulas, why not? So this is going to be A22, A33 minus A32, A23. And then just expand each of those, and then you got yourself a formula. A12, A21, A2, oops, actually work it out. A21, A33 minus A31, A23, and then A13, A21, A23 minus A31, A22. And you can distribute those constants around and shuffle them around, but you'll see that there's not really anything striking about these numbers that you can try to remember it easily. So I would always probably come back to the idea about expanding one of these things. Yeah.
How do you know which A to add and which A to subtract? Other elements?
The A's that you're adding and subtracting are based on these numbers over here. So the A11 has a positive, the A12 has a negative, the A13 has a positive.
Okay, so it's
Based on
entirely
all-
based on the matrix?
Yeah.
Whatever, okay.
Yeah. And the thing is that if you decide to go another route and say, oh, instead of expanding through the first row, you can expand through a column, like even the second column. We can expand on the second column. And then what you're going to do is you're going to start from here, and that has a negative sign from the beginning, so you'll start with a negative. So it's going to be A12 times the determinant, if you cross this out, is going to be A21, A23, A31, A33. Plus, the next one down is a positive, A22, and then you cross the row and column out, A11, A13, A31, A31, the last one is going to be a minus, that's A23 or A32. And then you cross out the row and column that this is in, you're going to get A11, A13, A21, A23. And then you can go on and work this out. So, did I do something wrong?
I don't think
Okay.
so.
So, Tom.
This all seems well and good. Why do we do that?
Just so we can find a determinant.
Well, I mean, like, why does it look like that? Because like I have no intuitive reason for why I would believe like that would give you the same number as that. This seems like a kind of arbitrary game.
Well, first of all, it should give you the same number, and second of all, this allows us some freedom to decide which row or column to expand on based on if any of these numbers happen to be zeros. So if I happen to have like a row of zeros here, except maybe for that one, I might decide I want to expand on this last one.
Yeah, but like, I mean, just like, why does it work like this?
Oh, why does it work like that?
Why do you have these alternating plus and minuses? Why do you get to cross out rows and columns, and it all just magically works out if you play this game with the same number?
Yeah, I don't know.
Like, well, it's just like, let me try a bunch of this stuff.
I believe you. I've done these.
Yeah.
You made us do them in differential equations.
Ooh. Ronskins.
Yeah, that guy. And
Well,
I believe you. It seems really, really arbitrary.
it seems arbitrary, but that's the nice thing about these matrices is that there's these A matrix that we have. They're actually called, I don't know if they're called cofactors or something associated with it is called cofactors, but the idea of cofactors is really embedded in matrices. That's why there's a lot more interesting things about matrices, and aside from solving systems of linear equations. And so they have a lot more treasures in them. They have a lot more value. They have a lot more significance than one would just see at the very beginning. If you study matrices, you see that the diagonals are special. The sum or product of the diagonals are something. Upper triangular, lower triangular matrices mean something.
Should we start to get into that?
Very little.
Oh.
One of my students from last semester is actually starting up. I think she's going to UCLA, and she's taking an advanced linear algebra class. So I'll talk to her and see what kinds of things that they cover there. Might be interesting to throw in at you guys.
Okay.
Matt, you have questions?
Yeah, I think it was more about
Similar to
yeah.
philosophical type. Alex?
When we're choosing to expand, we want to expand over the zeros, or do we want to include the zeros?
You want to expand through the zeros. So like if I have the second row has a couple of zeros in there, so I definitely want to expand where there are zeros, whether it be rows or columns, because that'll just guarantee a couple of things to disappear and I don't have to worry about it.
You want that help with larger matrices?
Yes, very much so. And so the process for a 3x3 matrix is going to generalize to a process for a 4x4 or an n×n matrix. And it'll just help us get through the determinant faster. Yeah?
Does that mean there's ever a row and column where columns all zeros? It's all zero?
If you had a whole row or a whole column full of zeros, then automatically zeros, because if you expand on that row or column, everything's zero. Not only that, by what?
Isn't it linearly dependent?
Then the columns and or rows are going to be linearly dependent because of the inverse matrix theorem. There's all the theories going to start tumbling down on you. I mean, in a good way. I don't mean the tumbling down is not good.
But if there's a row of zeros, you can't do it, right? You can't. You just
Well, that's the thing, is that if there's a row of zeros, then the determinant is zero, and then you're done. And you don't even have to mess with it.
You actually want to pick the row of zeros to find your determinant.
You want to pick the row with the most zeros if there is a row of the most zeros.
Yes, ma'am.
All right, so let's define, here's a definition of a cofactor. given A equals, so I should put, so the Aij with the brackets, let's just say that's the representation for the whole matrix. You can think about it as this. And then this could be any size matrix, not just a 3 by 3, but it could be any n by n. It should be a square matrix though. The Ij cofactor. So that's what we're defining. The Ij cofactor of A is a number, C sub j. C sub ij, and that's equal to, so this is now going to account for this thing that we're multiplying by when we expand. It's going to be positive or negative depending on where you are, and the quick mathematical way for figuring out whether you're positive or negative is that if you're in if you add the column and the row that you're in, and if that number is even, then you're a plus. If that number is odd, then you're at a minus. So that takes care of that. And then you're going to take the determinant of your Ij matrix, and that's the Ij's that when you, the submatrix where you cross out the ith row and the jth column. So Cij would be essentially the sign that comes here and the determinant of the matrix, because the Cij accounts for the sign too. So this is the more mathematical way we want to think about this.
So instead of remembering plus, minus, plus, and whatnot,
yeah, you can just remember this. But I would say it's easier to remember the plus, minus, plus this way and expand it this way. This is just the formal definition for a cofactor, which is used a lot in like more advanced linear algebra.
so what is the cofactor for a matrix?
It's this. By definition, it's the determinant of the submatrix with a positive or negative taken into consideration.
No matter how large a matrix we have, is it always going to follow this plus minus plus pattern?
Yeah, no matter how large. And then as you do this, you know, for a 4 by 4, when you do this, you'll have 3 by 3s, and each one you'll do that also.
They still make us do that also.
I
don't like the way you just laughed.
Matrix determinant.
You shut your damn mouth.
But see, this is the idea though. This is because now this is a more systematic way of looking at it. This is something that a computer can do. You can have a computer pick out your Ij, your A, capital A sub Ij matrix, and then you can have your computer figure this out, and then you can do some sort of recursive calling of the thing. Although that's not exactly what they use in real life situation, but that would be a fun project for people. I mean, computer science people. So this is, I'm writing the same thing in slightly different words. I guess say without ith row and jth column. So that's just the name, so that now we can rewrite our determinant for an n by n matrix, so that we can say determinant. Ooh, copy 10. I'll leave it for other people to use. So determinant of the n by n matrix is going to be, oh, I wrote this differently. So expanding on the first row. And remember that you can expand on any row or column, but just say if we're expanding on the first row, just to keep things simple, determinant of A is going to equal to stuff. So I guess I don't know if I want to use I, let's use K. K goes from 1 to N, assuming we're an N by N matrix. And again, if you're using computer science stuff, this would be 0 to N minus 1. So A sub, we're expanding through the first row, so it's just going to be sub 1, and then these are going to be the columns times C sub 1K. And C sub 1K will have either positive or negative, and then it'll have the determinant of this submatrix. So it turns out that if we can define this cofactor, we can have a nicer formula for the determinant of the matrix, but then that formula is not really that useful practically when we're actually trying to compute it. Of course, practically when you're actually trying to compute it, you'll probably just use a computer anyways. But if you were to do it by hand, it's better to think about it this way instead of the more theoretical way of including the cofactor idea. In fact, somebody tried to do the cofactor in the test for like a 5 by 5 matrix, and it just kind of confused me a little bit trying to follow the work. So there's a theorem that says you can expand on, we've been saying that we're expanding on a specific row or column. We're expanding on the first row of these examples that we're coming up with, but there's a theorem that says you can expand on any row or any column. And I think this is theorem 1. I want to be formal here. The determinant of a matrix column can be computed by a cofactor expansion across any row or any column. Let's just say that then. The determinant of an N by N matrix can be, what did I say? Can be computed by expanding on any row or column.
Matter of choosing which is most convenient.
Well, the choice is up to you, and some are easier than others, and some doesn't make a difference which one's which. So if we have our quiz question over here, it's 1, 4, minus 2, 0, 1, minus 2, 5, 0, 3, 0, 5, 0, 0, 0, 0, 1. What would you be interested in expanding on?
0, 0, 0, 1.
0, 0, which one? There's 2 of them.
Either or.
It's in the
I like the right
The bottom one.
column.
So it doesn't really matter because it's going to be probably almost the same amount of work, at least for the first step, right? So if we expand on like the row or the column, we know that in the beginning we'll have a bunch of zeros to work with. And so let's take a look at that. So let's make sure that we have the pluses and minus figured out. So plus, minus, plus, minus. So we start off with a minus here, but that's going to be 0 anyways. And so I'm not going to care what the cofactor is or the submatrix is because it's going to disappear. So we can just move on to the next one. This is a plus, another 0. another 0. So all this doesn't matter until we get to that last one. Plus. So once we get to that last one, we would say, hey, let's figure out the submatrix. Let's cross out the row and column. So we cross out the row and column, and we have this submatrix here. So this one is not full of zeros, but then there's at least one 0 that we can take a look at. So that's 1, 4, minus 2, 1, minus 2, 5, 3, 5. So there's a 0 here. I'm interested in exploiting that. We can either do last row or second column. And then in doing so, we'll do this as part of this work over here, or off to the side, or wherever you want to do this. Any suggestions?
Second column.
Second column, let's go down the column. So plus, minus, we're starting off with a minus again. Minus 4, and then what's left after you cross out the 4? 1, 5, 3, 5. And then the next one is a plus, but this was actually a negative 2. And then 1, negative 2, 3, 5. And then this is our last one, which is a 0, so we don't care about the submatrix from there. And then now we figure out what these things are, but they're 2 by 2 matrices, so that we can just use our original formula for the 2 by 2 matrices. So this is going to be 5 minus 15, and this is going to be 5 minus negative 6. So what do we have here? We have minus 4 times negative 10 minus 2 times negative 1.
11.
11.
Positive 11.
Positive 11. Something like that. This is positive 40 minus 22, which is what? 18. So this is 18, and then you have 18 times 1 is 18. So the determinant of that is 18. First, it's not 0, so we know that the rows are linearly independent, and it has an inverse if we decide that we wanted to find an inverse, and all those other things that follow in the inverse matrix there. Yeah.
I just got to thinking, if we really wanted to, could we manufacture like some zeros within that process somehow?
Sure.
Like through row reduction maybe, or
Yeah. Well, you did it, right? I mean, there's no space.
Oh wait, but would that give you the same determinant?
I don't know.
If you took a matrix and row reduced it a bunch? Or
It should
factored
be.
it?
I mean, if it's an upper or lower triangular matrix, I think it would work.
Huh.
If you multiply the diagonals together.
That's a good question.
Well, wait, no, I don't think it would, because
Well, you can't have.
every matrix that that's invertible, you could reduce down to the identity matrix for that thing.
Correct.
So then, if every matrix, so if you could row reduce something and the determinant was the same, that would mean, since you could reduce them all down to the identity matrix, they would all have the determinant of the identity matrix, so every invertible matrix would have to have the same determinant.
Every invertible matrix has. Oh yeah, every invertible.
So I don't think that would work.
Yeah, I don't know if that would work like that.
That wasn't exactly what I meant.
No.
But you meant something else that might, so I guess Alan might have taken it too far, but if we try to go back to what you were
Never
thinking.
do that.
It's possible. I mean, we have the LU factorization.
You have the LU factorization, right? So We'll dig into the LU factorization, but for the LU factorization, you remember that the last part of the LU factorization, you find your U, which is an upper triangular, and then you have an L. Do you remember where the L came from?
Your elementary.
L, inverses of all elementary matrices. So let's take a look at some elementary matrices. There's one kind of elementary matrix that we use a lot. That's the adding business, right? So let's say add, well, we multiply. First we multiply by something. So let's do multiply row 1. Oh, why don't I use my other A, B, C, D, F, A. I need the letter. G times row 1 plus row 2. Let's work with a simple addition of something, and let's use a 4x4 matrix. On a 4x4 matrix, this matrix should look like you take row 1, 1, 0, 0, 0, to row 2. G, 1, 0, 0, 0, 0, 0, 0, 0. All right. Let's go through the finding the determinant of this thing. So we see there's plenty of zeros to work with here, right? And so I would not want to do the first row or the second, or the first column or the second row, because that's going to give me two things. So I'll just pick one of them. What should we expand with? Let's find the determinant of this. Bottom row. So let's expand through the bottom row. Plus, minus, plus, minus. We start off with a minus 0 times something, doesn't matter, plus 0 times something that doesn't matter, minus 0 times something that doesn't matter, plus 1. Here we go. Ooh. Times a submatrix. 1, 0, 0, G, 1, 0, 0, 0, 1. Okay, let's expand through. Now we're doing with this, everything else is 0, that's cool. Let's expand through first row or last column. Yeah. Bottom row again. So we got plus, minus, plus. This time we're starting with a plus. Minus, plus. And then we have a smaller matrix. And what's the determinant of that? 1 minus G times 0, which is 1. And so the determinant of this turns out is 1. Now I didn't say that this is most general, but this is pretty general. What if we would have done some other thing? What do you think our determinant would be?
It's supposed to be 1.
It's still going to be 1. And so here are a couple of other clues. This is a lower triangular. I mean, there's just this one G over here that made it lower triangular. So it turns out that if you have any upper triangular matrix or any lower triangular matrix, if you imagine expanding on one of the rows and then you have a smaller set, it's still going to be an upper or lower triangular matrix. And then you expand on the bottom row again, you'll still get an upper or lower triangular matrix. And so it turns out that another theorem that doesn't come up for until a little bit later, but we can say it now, that if you have an upper triangular matrix or lower triangular matrix, I think so, yeah. So it's really just the product of the diagonals. And in this case, for an elementary matrix, since it's either upper or lower triangular depending on how you're adding something for this particular elementary matrix, then your determinant is always going to be 1. That's interesting. So let's take a look at another elementary matrix. Let's multiply the elementary matrix. Let's multiply one of the rows by G. It doesn't have to be the first row, but it could be any row. But let's take a look at the first row. Find the determinant of that, and if we know this little rule already, what can we say about the determinant of this? It's just going to be whatever you multiplied by, right? That's another interesting fact. There's one more type of elementary matrix, and which one is that? Swaps. So let's swap the first 2 rows and see what kind of a matrix we're going to get. So this is no longer an upper or lower triangular matrix because we have a 1 in the upper side and a 1 on the lower side. So we have to actually do an expansion. So let's do what we did before. Let's keep expanding on the bottom rows and see what happens. Because this bottom row has zeros, this bottom row has zeros, and then let's see. So if we expand on the bottom row, plus, minus, plus, minus, plus, minus, plus. So we start off with a minus. Minus 0, plus 0, minus 0, plus 1. Times your submatrix. 0, 1, 0, 1, 0, 0, 0, 0, 1. Should have vertical lines here because we're talking about submatrix. Now we'll expand in the bottom again. Plus, minus, plus. So we start off with a plus this time. 0 times star minus 0 times star. And then plus 1 times 0, 1, 1, 0. Now it's a 2 by 2 matrix. What's the determinant of this?
-1.
This is -1 this time. So -1 times 1 over there times 1 over here is just going to be a -1. So the determinant of this type of an elementary row operation is -1. So your determinants are either 1, -1 if you do a swap, or is equal to G if you happen to multiply one of the rows by something. Yeah.
So that negative 1 mean? For that matrix.
The negative 1 just means that's the determinant, which means it's negative 1.
Just negative 1.
Yeah.
If we have anything in this form, it might be easier to just, it might save some time on expanding.
Yeah, it might save some time on expanding. So, there's another important theorem that we're going to use, not really prove so much, but I don't know what number this is in the book. I think this is theorem number 6 in the book, so there's like 3, 4, and 5 that we kind of skipped over. Turns out that the determinant of the product is a product of the determinants, which is a nice, really important piece of property for us. And that would help us when we're kind of puts into perspective the stuff that we've been doing. Oh, so by the way, this stuff on the elementary matrices is theorem 3 in your book, and then theorem 4 is something about the invertible stuff, which we won't worry about because it'll come out in the next big theorem when we talk about the invertible matrix theorem. And then the transposes, determinant of the transpose is equal to just the determinant of A. So it's one more theorem here. Theorem 5. Sorry, I'm writing this backwards. Determinant A transpose is equal to determinant. So when you do the transpose, you're switching rows and columns, but if you're expanding on a row and expanding on a column, and you were saying that that's the same thing, and it doesn't really matter how we expand. So without much proof, that's basically the explanation for that theorem. But that theorem number 6 is important because now with these elementary matrices, we can get to the row reducing. And when we row reduce, right? When we row reduce, then we come up with an upper triangular matrix. And if you have an upper triangular matrix, it's just a product of the diagonal. So if you row reduce this, let's take somebody's row reduction. Hopefully they did it right. So the upper triangular matrix that this person got, if it's correct, is 1, 4, minus 2, 0, 0, minus 6, 7, 0, 0, 0, minus 3, 0, 0, 0, 0, 1. The lower triangular is a unit. Lower triangular. So there's a bunch of 1s here, right? And it's an upper triangular or lower triangular matrix. So the determinant of this thing is going to be 1. What's the product of the diagonals there? 18. Which is what we got. All right. We don't have class on Wednesday. So I do want to know about the honors. If you're interested, send me an email so I can send you a form. And on next Monday, we'll finalize our form.